And now that we have determined the project completion time and also have scheduled individual activities, both critical and non-critical activities, now let's turn our attention to computing probabilities for project completion. Okay. So in PERT, each activity has three times, right? Optimistic, pessimistic, and most likely. From those three times, we were able to compute variance for each activity. Okay. Now, when we look at the project completion time is given by the critical path. Okay. It is not given by all the activities. Even though all the activities must be completed, the completion time of the project is given by adding the expected activity times along the critical path. So to find the variance associated with the project completion time, we must sum the variances of only the critical activities along that path which gave us the project completion time in the first place. So that's a very critical point to note. You should not add up all the variances. You should add only the variances of the activities on the critical path. So when you add that, you get a path variance. Okay, so here these are the critical activities. So add those variances, you get the project variance. And you take a square root of that and you get project standard deviation. So now with this, we get the expected project completion time. So that is like the mu in a normal distribution. And then we have the standard deviation of that project completion time. So with that, we can use the normal distribution to find the probability. One might ask, we assumed each activity time follows a beta distribution, so why are we using normal distribution for project completion time? So it turns out that when you add beta distribution values, which is what we did, right? We took the expected time for each activity and added them up to find the project completion time. When you do that, okay, when you add a bunch of numbers coming from any probability distribution, the resulting sum will follow normal distribution, approximately normal. That's what is called central limit theorem. Okay. Larger the number, the more closer the probability distribution will be to the normal distribution. So that is, even if the activities follow some crazy distribution, it will still be true that the sum will be normal distribution. But in this case, we are assuming beta distribution. So beta distribution is very similar to normal distribution, except that it is not symmetric like normal distribution. It's very close. And therefore, even for small number of activity times following beta distribution, the sum will be normal. So even for 4 or 5 activities, it will be normal. But in real life project management cases, the critical path will have probably hundreds of activities, so there will be no problem assuming or using normal distribution to compute probability. So here we take the project completion time that we found from scheduling and the standard deviation that we calculated, and then compute a z, okay, due date minus the expected time divided by the standard deviation, and find the probability using normal distribution. Okay, so let's look at an example. Okay, so this is the table that we completed. Okay, so expected finish time is that. Okay, variance is sum product of the critical activities with the variance. So if you do a sum product of that, all the non-critical activities will get zeroed out because you will multiply with 0, and the critical activities will get multiplied by 1, so it will get picked up. We already computed this here. Okay, so 3.11, so which is what we get here as well, obviously. And standard deviation is square root of that. So once we have that, then we can find the probability. So you have a due date. So remember, due date was 16 weeks. The environmental agency gave them 16 weeks to get it completed. So what is the probability that we will finish this by 15 weeks, so we can use, okay, you can use Z and then normal distribution, or you can directly use norm.dist. We did this in way back in chapter 2, I believe, the probability chapter. So this is the due date, comma, mean is the expected time, comma, standard deviation, and then you have to specify whether you want cumulative or false would be probability mass function, which is the height of the curve. So you should always use 1 for probability. So this will give you cumulative probability. So the probability that the due date will be 16, or I'm sorry, the completion time will be 16 or less than 16. So that's your probability. And if you want the probability that you will not meet the deadline, then it will be 1 minus this. So probability of completion within the due date is that. Yeah. We can use the other way around. Suppose we want to set the due date for a probability of confidence probability. Suppose we want to be confident at the 95% level, for example. Okay. Then what should be the due date for that? Okay. Due date for 95% confidence will be norm.inv, and then the probability. Okay, so it's cumulative probability that you should use. Okay, mean and standard deviation. So that will give you 17.9. If 17.9 is the due date, then you will have 95% confidence that you will finish the project by the due date. Okay. So if you wanted to use Z, and then it's okay, like for example, the way it is set up in the PowerPoint, so it will be due date minus expected time divided by the standard deviation. So that will give you the Z, and then you can use norm.s.dist will be cumulative, Z and then cumulative. So it will obviously give you the same probability value. And same here too, you can find Z first for the given probability. So that will be norm.s.inv, which will be that probability. So this will give you the value of Z. And once you have the value of Z, then the due date will be mu, which is the expected time, plus Z times the standard deviation. Okay. Obviously, that's going to be the same answer as that.